Dear students, in today's video we are going to discuss what are electric field lines and their properties. First of all, let us know that electric field lines are not real lines. Electric field lines are imaginary. They can be straight or curved. Here in this figure we have drawn our electric field line. This is our electric field line in red color. It is a curved line. As you can see, it's not a straight one, it's a curved line. We have chosen a point P on this line and draw a tangent corresponding to it. Then we choose a point Q on this line and the tangent is EQ. When you draw a tangent to the electric field line, it gives you the direction of electric field at that particular point. So, the tangent drawn at any point on the electric field line gives us the direction of electric field intensity. So, for the point P, the electric field direction is represented by vector EP vector, and for the point Q, the direction of the electric field is EQ vector. And we know that the electric field and the force have same direction. If we bring any trace charge in this electric field EQ, then the force experienced will have the same direction as that of the electric field. Next is, how do you actually define electric field line? Electric field line can be defined as a path along which a unit positive charge means a charge of +1 coulomb. Charge actually moves in the electrostatic field if it is free to do so. So, let us consider a field and +1 coulomb charge. The trajectory followed by this +1 coulomb charge represents the electric field line. Then we know that the charges are of two types. One are the positive charges and another one are the negative charges. So, electric field lines due to positive charge are directed radially outward. We have chosen a positive Q charge here. It's a positive charge and 4 electric field lines are coming out from it. 1, 2, 3, 4. Right? Arrow is put on the line and it is in the outward direction. Right? So, electric field line due to positive charge are directed radially outward. Then we choose another charge and out of this charge 1, 2, 3, 4, 5, 6, 7, 8. 8 electric field lines are coming out, right? If the first charge was plus Q with 4 field lines, now the number of field lines are double for the second charge. In the first charge case you have 4 and in the second charge case you have total 8 lines. Then if the first charge was plus Q, it means that this particular second charge will be double in magnitude, right? Then we have electric field lines due to negative charge. Then due to negative charge, the lines are directed inward. The lines moves toward the charge. They are directed inward. Similarly, we compare the things. For the minus Q charge, we have 4 lines, and for the minus 2Q charge, the charge magnitude has doubled. So, we have total 8 field lines. From here, we can say that the magnitude of the charge is directly dependent to the number of field lines. So, the magnitude of the field is represented by the density of the field lines. Higher the charge, more will be the number of lines. More will be the number of lines means the lines are placed densely. Their density is high, right? Now, when you draw some charge, say I draw plus Q charge, I say that the lines are directed outward. So, you will experience this thing that closer to the charge, the lines are at smaller distance. The distance between the lines is less. As I move away from the charge, the distance between the lines has increased. So near the charge, the lines are closer, so density of lines is more, hence the electric field is stronger. As you move away from the charge, the lines are separated by a large distance. As we have drawn it in with the green color, density of lines is less. Then it means that away from the charge, the electric field is weaker. This particular thing can be understood with the help of this figure too. This is the first charge from where you can see total 8 lines are coming. From the second B charge, we have 16 lines are coming, almost double. For the next one, it will be obvious 32 lines are coming out of it, right? So, what you see that if you measure the electric field, then electric field from the C charge is greater. Why greater? Because density of lines is high. Density of lines is higher in case of charge C. It means that EC is greater than EB because it has 32 and it has 16. Then for the first charge you have 8 lines. It means that EA is smaller as compared to EB and EB is further smaller as compared to EC. Next we discuss the electric field lines due to a dipole. What is dipole? Dipole means equal and opposite charges, means both charges are QQ but they are opposite. One of them is minus Q, another one of them is plus Q, separated by a distance. Usually we represent the distance as 2A, 2x, 2L, right? So this is the dipole. We want to draw the electric field lines corresponding to the dipole. One charge is plus Q, which is placed over here. Another charge minus Q, which is drawn in red color. So we know that from the positive charge, the electric field lines are directed outward, right? So these are the electric field lines which are directed outward from the positive charge, right? And for the negative charge, the lines are directed inward. These are the lines which are directed inward towards the negative charge. So the electric field lines start from the positive charge and they ends at the negative charge. So here you can see that the electric field lines are starting from the positive charge and they are ending at the negative charge. One thing is to be noted that when you are moving away from the charges, the distance between the lines is increasing. When you are away from the charge, the electric field is less. It means that the distance between the electric field lines will increase, their density will decrease because you can't experience the same electric field, same potential of charge as you experience the closer to that particular charge. When you are away, the effect will reduce. Next are the electric field lines due to like charges. We have two charges. One charge is plus Q, another charge is again plus Q. Both the charges are of equal magnitude. So the electric field lines starts from the first charge and they are moving upward because both the charges exert lateral pressure on the field lines of each other. Similarly, this line is coming outward from the charge. When they come closer to this particular line, then they exert pressure on each other and they start bending toward this particular line. Similarly, the second line will start from here. It will again experience the repulsion force from the second charge as the like charges repel each other. So the lines are repelling each other. So in this case we have Q1 is equal to Q2. Both the charges are positive charges. They exert lateral pressure on each other, which is responsible for the repulsion between the like charges. we have a point P at the center of the line joining these two charges, and at this particular point the net electric field is 0. Means whatever the field is coming from this positive charge, it is cancelled out by the field coming from the second positive charge. At this particular point the electric field is 0. The next case is for both the charges are negative. The first charge is minus q and another charge is again minus q. Both the charges are negative but they are equal in magnitude. The only difference is that the arrows are put inward. As you can say, in this case the arrows were outward, away from the charge. The lines were moving away from the charge with the arrow. In this case the lines are moving toward the charge. The arrows put on the lines are toward the charge. Similarly, again for the minus q and minus q charge, the neutral point is at the center, and at this neutral point the electric field is 0. Now the next situation, when you have two charges such that one charge is q1, another charge is q2, but the charges are not equal. The first one charge q1 is higher in magnitude as compared to the charge q2. It means that q1 is a stronger charge. It will have electric field lines moving from it, and they can move up to greater extent as compared to the charge q2, which is weaker, right? So the field lines of q1 are moving out from it. Similarly, the field lines from q2 are coming out from it, but being q2 smaller in the magnitude, it has less density of field lines. It has less number of field lines as compared to the q1. So 2 points are here. q2 has smaller magnitude, so it has less number of field lines, while q1 has larger magnitude, it has large number of field lines. Moreover, the distance travelled by the field lines from the q1 charge is large. Due to that larger distance travelling, it has shifted the neutral point towards the q2. P is the neutral point, but it is lying toward the q2. So the neutral point P lies closer to the smaller charge. It is very important to understand this thing. When you have two charges, they are like charges, means both charges are positive, right? And then during that situation, one of the charge is greater magnitude, means q1 has greater magnitude, so the neutral point will shift toward the q2, which is a smaller charge. So the neutral point moves toward the smaller charge. So electric field lines from the charge q1 travels up to a greater extent due to the high strength of the charge. That's what we discussed. The lines of q2 charge exert lateral pressure on the lines due to q1. Hence, these two charges repel each other, and the neutral point lies closer to the smaller charge. The neutral point lies closer to the smaller charge. Next are the electric field lines due to a charge sheet. We have a positively charged sheet. This is the charge which is uniformly charged positive throughout. The field lines are directed away from it. These lines are parallel and straight. They are equispaced, means distance between these two lines is a. Then for the another line, distance is again a, and they will continue to keep on moving with the distance a. They are equispaced, and the field produced by these lines will be uniform, means if you measure the magnitude and strength of field at any point inside these lines, they will be same. Uniform field means the field will remain same throughout. Then if you are discussing the uniform field, then you should know what are the non-uniform fields. So for the uniform fields, the lines will be parallel and they will be equally spaced. then you will have a uniform electric field. So if this is point P, this is Q and this is R, and the electric field at point P will be equal to Q and will be equal to R, right? If you draw lines like this and these lines are not parallel, means these lines are not parallel, not even equispaced. The difference between these lines, here the distance is large, here the distance between the lines is small. This, if I say this is x1, then this is x2, means my x1 is higher as compared to x2. Then the electric field at point A is not equal to B and is not equal to C, right? The third case, we assume that if the lines are curved one, like this, the lines are curved but they are equally spaced, then even this will come under the category of non-uniform field. Why non-uniform? If the distance is same, x, but at any point, if I draw the tangent, suppose here I draw a tangent, it will have this direction, for this point it will have this direction, for third this one, and for this one, means for each line tangent will have different direction. If direction is different and electric field is a vector quantity, direction is changing, it means the electric field is changing, and if the electric field is changing, means that it is not uniform throughout, means it is a non-uniform field. Next is, the electric field has following properties, that these are continuous curve. They start from the positive charge and ends at the negative charge, which we have seen while drawing the electric field lines from a dipole. They have started from the plus Q charge and they have ended at the minus Q charge. Now the next is, no electric field line is present inside the conductor. If you have a conductor, right, then inside this conductor no electric field line is present, no field line is present, and these field lines are perpendicular to the conductor. The field lines are perpendicular to the conductor. If you have any conductor and it has field line on it, then it will make an angle of 90 degree on the surface of the conductor. If you assume that field line is having this kind of orientation on the conductor, then this field line is not possible. This is not allowed. The field line cannot have this kind of orientation on the conductor. This is not allowed. This is not allowed. Only the field line can make perpendicular alignment on the conductor, means they are always normal to the surface of the conductor. Next is, electric field lines do not form closed loops. Electric field lines start from positive charge and ends at negative charge. This can be seen in case of electric dipole. One charge is plus Q charge and another charge is minus Q charge. We draw the electric field lines they are starting from positive charge and ending at negative charge. For a single point charge plus Q, electric field lines are straight lines. They move away from plus Q charge and go up to infinity. For minus Q charge, the lines are again straight lines. They move toward minus Q charge. For forming the closed loop, it is required that you have a charge. Say we have a charge plus Q. The electric field line start from plus Q charge and end at plus Q charge. This will make a closed loop if the field line start from a single point charge and it terminate on the same point charge, but this is not possible. So electric field lines do not form closed loops. The next thing is, this is the common question. It can be asked in your board exam, and it can be put in the form of an objective question during your entrance exam, that two electric field lines cannot intersect each other. Because if you draw two electric field lines, this is first field line and this one is the second field line. They are crossing each other at point P. If you draw tangent corresponding to this, then one tangent can be in direction A for the first field line. The tangent will be this one, and for the second field line the tangent will be this one, right? So at particular point P, it has two directions, which is not possible. So because at point of intersection we can draw two tangents, means two directions at a point, which is not possible. That's why the electric field lines cannot intersect each other.